Let's get started. So today's going to be the last day we lecture before we have an exam on Wednesday. So my goal is to get through chapter 3 today. I doubt we'll start any of chapter 4. So the exam will consist of content from chapters 1 through chapters 3. I'd like to end a little bit early today so that we can review. And that review is going to consist of you guys asking questions about specific content that you have questions about, not like, will this be on the exam type stuff, right? The exam, I think, I haven't completely written it yet. I think it will consist of about 40 multiple choice items. And then I think this time for the written part of it, I'm going to have 5 short answers, and you'll just write 4 of them. So of those 5, you'll choose 4 that you want to answer. Okay, we'll talk a little bit more about the exam at the end of lecture today. So I wanted to start by reviewing the biologically important molecules that we've already gone over. That is what of chapter 3 we've already begun to cover. So we covered carbohydrates, and we started with the lipids, the dietary fats specifically, right? So help me remember, first of all, in animals, what's the primary function of carbohydrates? Short-term energy storage. And the monomer of carbohydrates, like polysaccharides, was what? Do you remember?
Monosaccharides.
Monosaccharides. Exactly right. I feel like that's the easiest of the monomers to remember. It actually starts with a mono. So it's mono, single, saccharide. And then when we connect 2 monosaccharides together, we use a process called dehydration synthesis. And that dehydration synthesis takes out water, and it forms a special bond between those 2 monosaccharides. And that bond is called what?
Glycosidic.
The glycosidic linkage. Good. Okay, so before we move on to lipids, I'm going to talk a little bit about monosaccharides, dehydration synthesis. So this is glucose, right? And glucose has 6 carbons in it. And we said that all monosaccharides have the same basic chemical formula. That for every 1 carbon, there were 2 hydrogens and 1 oxygen, right? So if there are 6 carbons in glucose, how many hydrogens and oxygens ought there to be? 12 and 6. So if we have 2 glucose molecules, this one should have the same chemical formula as this one, right? So collectively, between the 2, how many carbons should there be? 12, right? 6 of 6 is 12. Hydrogens, there should be 24, and oxygens, there should be 12 as well, right? But if we do dehydration synthesis, all of a sudden we're going to change the relative ratio of carbons, hydrogens, and oxygens. Okay, so before dehydration synthesis, the sum total across these 2 molecules is C is equal to 12, H is equal to 24, O is equal to 12. What's it going to be after dehydration synthesis? To begin with, let's just diagram dehydration synthesis between these 2 glucose molecules. Do you guys remember how it goes? What do you want to pull off of this one?
The OH.
Okay, so let's take off this whole OH. Like this. Right? And then what are we going to take off of this one?
The H.
And there are 2 options here. We can take an H off here, or we can take an H off there. Which one do you want to do?
The bottom.
The bottom one. Yeah, let's do the bottom one. Because that glycosidic linkage has an oxygen in between the 2 carbons. So we're going to take this hydrogen off right here. So between these 3 atoms, right, the oxygen, hydrogen, and the hydrogen, we've created H2O. And then we're going to stick this carbon that oxygen, right? So that's the covalent bond that we're going to have. So we've taken 2 hydrogens from those 2 molecules and an oxygen. So after we've stuck these 2 things together with the covalent bond, what's the resultant chemical formula? What's that?
The H2.
H2O is going to be taken out, yep. So how many carbons are going to be left, how many hydrogens are going to be left, and how many oxygens are going to be left?
There's going to be 12 carbon, right?
Okay, so the carbons don't change, right? So these 2 together are going to have C12, H, how many?
22.
Why 22?
Because you take out 2
Because
hydrogens.
you're taking out 2 hydrogens right there. So we have H22, and we have O11.
11.
Why again? Because we've taken out another oxygen, right? So we have O11. I feel like if I was to give you guys a chemical formula of a polysaccharide and tell you what the monomer was, you guys should be able to tell me how many times dehydration synthesis has occurred. Let me give you an example. And I'm going to kind of make this up right now, so it may or may not work, but I think that it will. And I'll do it over here so that you guys can take pictures of that if you want. So let's say we have, give me just a second. I've already messed up. I think that works. So, let's say we have that polysaccharide right there. C30H55O25. The question is, how many monosaccharides are stuck together, and how many times has dehydration synthesis occurred? So what do you think? If the monomer is glucose, right? So it's C6H12O6 to begin with.
There's 5 monomers, right?
There are 5 what?
Monosaccharides.
Is it 5 monosaccharides? 5 dehydration synthesis has occurred, right? Because we're missing 5 oxygens, and we're missing 10. Well, that should be different, right? That should be 50. That's probably what messed you guys up. So the carbons stay the same, right? Because carbons, nothing happens to the carbons. So what we can do from this is we can say, okay, if we know our monomer, glucose, consists of 6 carbons, how many monomers are stuck together? So that's a simple division exercise, right? We could take 30 and divide that by 6, and that gives us,
5.
right, 5. Oh, I've already messed it up again. Dang it. So if there are 5, really what that should be is 52 and 27. Is that right? Nope, that's not right. 26. Yep, that's right. That's going to be my final answer right there. I'm going to do another one, and I'm going to get my math correct on this next one.
So number 5 is telling us how many times it's gone through dehydration synthesis.
So that 5 is how many monomers,
Okay.
right?
Mm-hmm.
And so if there are 5 monomers, how many dehydration syntheses have there been to stick 5 molecules together?
Well, because 4.
There's 4.
Right, there are 4. 1, 2, 3, 4, 5 monosaccharides is what we started with, so there have to be 1, 2, 3, 4 bonds, or 4 times that dehydration synthesis has occurred. Now we can also get at that mathematically, right? So we know that each time dehydration synthesis occurs, 2 hydrogens and 1 oxygen are removed. So if no dehydration synthesis had occurred, how many carbons, hydrogens, and oxygens would there be? We know that there would be C30, H60,
60,
and O
30.
30. But there aren't that many, right? How many oxygens have been pulled out?
4.
4. And how many hydrogens?
4.
It's close to
8.
4. 8, right? So if we have H8O4, how many water molecules is that? 4. Right? 1, 2, 3, 4 water molecules have been made. Which means that 4 dehydration syntheses have occurred. Let me do another one. I'm going to think about this a little bit longer, so just bear with me so that the math is actually correct. Okay, I'm pretty certain that one works. Here, instead of, however, a hexose sugar, a C6, we're starting with a pentose sugar. So each monomer of this polysaccharide consists of C5H10O5. Okay? It's basically the same thing as glucose. It has twice as many hydrogens as it has carbons and oxygens. We're just using a slightly different sugar to make a polysaccharide. So in this polysaccharide, how many pentose sugars are there? How many monomers are there? 5 of them, right? So there should be carbons, if no dehydration synthesis was to occur, there should be carbon 25, hydrogen, how many?
50.
50. And oxygen?
25.
25. But there aren't that many, right? So how many water molecules have we made when making this 4 of them?
4.
And how'd you get it 4, you guys?
Well, the O is originally supposed to have 25, so then I just subtracted it.
Oops. Yeah, so if we do this, right? 25 minus 21, we get 4. And if we get 50, take away 42, we get 8. And we know that H2O is a water molecule, so if we just kind of divide those numbers, we have 4 oxygens, 8 hydrogens, 4 water molecules. So how many times has dehydration synthesis occurred? 4 times. Exactly right. Are you guys, yeah, Carla?
So basically, you can usually tell if it's the same 1-to-1 ratio. You can tell how many dehydration it is just by knowing it's C25 and there's 5. And then you can double check your work.
Yeah, just by knowing the difference between carbons and oxygens alone should tell you how many times dehydration synthesis is occurred. Yeah, Adam.
So can you walk me through the terminology in that process? Because I know how to find what is which and stuff like that. If you know does that make sense?
So, no. What do you mean by terminology? Yeah, sorry. What do you mean by terminology?
Like, which one's dehydration? Like which one is which?
Okay.
Which process is which?
So there are 2 processes that we're concerned with.
Okay.
The first of which is dehydration synthesis.
Yeah.
And anytime there's a synthesis, we're making something. And dehydration means that we're pulling water out to make something, right? So in essence, what we've done is we've taken 5 pentose sugars. They look something like this, right?
Yeah.
And using dehydration synthesis, we've pulled water molecules collectively off of adjacent monomers, and we've stuck these things together.
Okay.
So that's dehydration synthesis. The opposite reaction is hydrolysis, and that's where we're actually going to take water molecules, we're going to split the water molecules apart, break these bonds, and attach hydrogens and oxygen and hydrogens to make monomers. Yeah. So those two processes are important, right? Because dehydration synthesis allows us to build big polysaccharides that allow us to store energy. So that's what glycogen is. It's just a big, long polysaccharide. And we can, on a short-term basis, store energy that way. However, when we actually need energy, then we have to go through hydrolysis and start breaking individual glucose molecules off and sending them to the correct cellular machinery to break those things down to create energy. Yeah, Carly?
Is it the same process to find how many times hydrolysis synthesis has occurred as a dehydration, just adding those?
Going the opposite direction? Yep. So I could say you're starting with this molecule, and you want to know how many monosaccharides you can make from that molecule using hydrolysis. And you guys could figure that out. Good question. Okay. Are there other questions about, because I can almost guarantee you, in fact, they've already written a question, that you're going to see something like this on the exam. This is your monomer, this is your polymer. How many times does dehydration synthesis occur? Questions on how to figure that out? Yeah, go ahead.
So like, when we get the 5, do we just, like, I'm just confused, like, how we got the 5, and then do we, like, out of every, like, number, do we divide that back out? I don't know.
Good question. So your question, I believe, if I'm interpreting it correctly, is how do we know that there are 5 monosaccharides that make that?
Mm-hmm.
Is that your question? Okay. So the easiest way to figure that out is, I will give you what the monomer looked like. So if this is the monomer, if this is that individual sugar, and there were 5 carbons, then all he needs to do is divide the total number of carbons, 25, by the monomer. And that should tell you how many you arrive at. So if each of these consists of 5 carbons, it's 5 times 1, 2, 3, 4, 5, 25
And then,
carbons.
so would we do the same for, like, 42? Like, what do we do for, like,
That's where it becomes a little bit more problematic, right? The reason that it works for carbons is because when we do dehydration synthesis, when we pull water molecule out, we're not pulling carbons off of those molecules. That number will remain the same. But the resultant polysaccharide will have fewer hydrogens and oxygens because we're making water molecules from those atoms. Yeah, Adam.
So each of those individual monomers make up the polysaccharide.
Right. Yep. So we use dehydration synthesis to connect monosaccharides, the